Okay, so again, well, how many remember calculus 2 when you learned about polar coordinates? I mean, you were used to in calculus 2, working in two-dimensional Cartesian coordinate system. Well, the Cartesian coordinate system, coordinates x, y, and then you learned about polar coordinates, where your coordinates weren't x, y anymore; they were r and theta, a radius and an angle. How many recall that in calculus 2, math 182? Okay, Samantha remembers it. Hung and Haley remember that, and you found that for certain functions, it was more convenient to do, like, for instance, integration using polar coordinates as opposed to Cartesian coordinates. So when we talk about coordinate systems, when we consider, we're used to the Cartesian coordinate system, x, y coordinates or x, y, z coordinates. When we consider other coordinate systems, it's because, given the framework of some application, another coordinate system is more convenient, just like in calculus 2, polar coordinates were more convenient. So like in our class here, like there's going to be, there's an example where it'll come up in the homework where you're dealing with a crystal lattice in chemistry for titanium, and you'll find that the standard basis vectors, that would be, I, j, and k vectors, or E1, E2, E1, E2, and E3 vectors. You'll see that those aren't the most convenient vectors for a basis. So I think, just to kind of get your head comfortable with this, I start with we'll just go with a simple example here. So I have a basis, B1 and B2, that is a little different than what you're used to. You're used to 1, 0, for two-dimensional space. You're used to the standard basis, 1, 0, and 0, 1. But remember, what are the conditions for a basis? Well, for a basis for two-dimensional space, the vectors have to span the two-dimensional space, R2, and also they need to be linearly independent. So sure, this here, the E1, E2 vector basis is called your standard basis. It's what you're used to. But this basis here with B1 and B2 is also a basis for R2. The vectors will span R2, and they are linearly independent. So what we want to do is we have this vector 1, 6, and we want to find the coordinates of that vector relative to the basis B. Okay, so now, like, relative to the standard basis, well, no, let's just do that. Okay, so in other words, let me see if I can make this a little bit simple here. So the vector x, 1, 6, equals 1 times E1 plus 6 times E2. Okay, where here's, the basis E1, E2. So the coordinates of the vector x relative to the standard basis that you're used to are 1 and 6. But we want to find the coordinates of the vector x relative to this basis B1 and B2. So the way we're going to start that is, we wish to find C1 and 2, these are going to be your coordinates, such that the vector 1, 6, the vector 1, 6 will equal C1 times B1 plus C2 times B2. Yes, question, Nafani? I think, did somebody have a question? Oh, you're good? All right, all right. I mean, this is, so, in order to answer this question, we need to have the right vector equation. Okay. And this is exactly what we're doing. If we want to find these coordinates, C1 and C2, the coordinates of the vector x relative to this new basis script b, we need to solve this vector equation. And so we set up the augmented matrix. We do a few row operations to get the augmented matrix in reduced echelon form. So I took 1/2 times the second row, put that result in the second row, and then I took -1 times the second row, added it to the first row, and replaced the first row with that result. And so we find then that our coordinates are going to be C1 equals -2 and C2 equals +3. All right, and so therefore, the coordinate vector of vector x relative to this basis b, okay, and remember the basis b was equal to basis vectors 1, 0 and 1, 2. Here's your B1, here B2. Okay, so the coordinate vector of the vector x, that vector 1, 6, relative to the basis script b, is going to equal -2, 3. And this notation here, this notation stands for the coordinate vector of x relative to this basis script b. See, we have to start using that notation because we're going to be dealing with different bases. We're going to be finding coordinates of vectors relative to different bases. Are there any questions so far? All right, may I move to the next page? I want to make sure I'm pacing myself okay. Maybe give me a thumbs up when you're ready. Okay, Nafani's good. Benjamin's good. Lewis is good. Wonderful, wonderful. So what I want to do is I want to geometrically help you understand what these coordinates -2 and 3 mean, okay, in this problem. So I drew a little picture here. I drew a little picture, and again, you can tap on it twice. And I mean, I think the picture is pretty good size, but you can tap on it twice if you need to, and to blow it up. But what I did was I drew my vector B1. I want to put it in red actually. Vector B1 is here. B1 was the vector 1, 0, and B2 was the vector 1, 2. Okay, so I drew those vectors, and then I also drew the vector 1, 6 right here. All right, and remember the coordinate vector of x relative to basis B was determined to be -2, 3. So what does that -2, 3 mean geometrically? Well, I mean, I want to see, I mean, I want to arrive from the origin. I want to arrive here at the coordinate 1, 6, right? I want to arrive at that coordinate. So that's 1, 6, right? All right, so what's going on? What's going on here? Can everybody see the green okay? Good. Good. Hold on. I mean, what am I doing here? What am I demonstrating here? With these green markings. I mean, here's the vector B2 right here. What would this vector here be? what would that vector be? Good, that would be 2b2. That would be 2b2. Good, Hung. Okay. So you can kind of see what I'm doing, right? And then one more gets me to 3b3. 3b2, sorry. So that gets me, if I, this is like, remember the problem where you had like you had to like move along the graph where it had the vectors on it, and you had to kind of move along the graph and find the right linear combination of vectors that gets you to the right vector. Well, I go up 3b3. Okay, so I went up, I did 3. I mean, my units now are not E1 and E2. My unit vectors are not like I and J. My unit vectors are vectors B1 and B2. So from the origin, I went 3 units, 3 B2 vector units, and that got me here. And now, okay, what's going on? What's going on here? What am I doing there to get to the 0.16? What did I do there in the yellow? Well, B1 is this vector here, right? But it looks like I'm taking the B1 vector and writing it in the opposite direction, right? Well, what would that vector be there? What would that vector be there? That wouldn't be B1, right, Nafani? It would be negative B1. So I do negative B1, and then I do another negative B1 here. And therefore, I went -2 units. I took the vector B1, and I moved 2 B1 units in the negative direction. And so that is how that's how these coordinates are coming about. And I got I know we're out of time here. I just want to show you one more thing real quick. It'll only take a few minutes. But is this picture helpful? Is this picture helpful to help you understand these what these coordinate vectors mean? Okay, thank you, Hung. Thank you, Benjamin. Excellent, Eleanor. Excellent, excellent. Thank you, Nafani. All right, may I go to the next page to finish this up? Okay, all right. So there's a thing also called a change of coordinates matrix that goes from the base B to the standard basis. Standard basis is the E1, E2 basis. That's this matrix here. And the matrix here, so if I were to take the coordinate matrix, if I were to take the coordinates of x relative to the basis script B, and the basis script B consists of vectors 1, 0, and 1, 2, right? If I were to multiply the change of coordinates matrix from the base B to the standard basis, and we denote that by P subscript B. If I were to take that change of coordinates matrix and multiply it by the coordinate vector of x relative to the basis b, that's going to equal the vector 1, 6. But remember, matrix multiplication, you learn you can write matrix multiplication, a matrix times a vector, you can write it this way, which is very helpful because you can see that the vector 1, 6 is simply equal to -2 times 1, 0, okay, which is -2 times b1, plus 3 times 1, 2. That's 3 times vector b2. So you demonstrated this geometrically on the previous page, but now you see it also algebraically. So the matrix, the change of coordinates matrix P sub B, P subscript B, sometimes I call it the peanut butter matrix. I don't know why, it just kind of helps me think about it. But the matrix, the change of coordinates matrix, P subscript B, transforms the coordinate vector x sub b into the vector x. So you're going back and forth between coordinate systems utilizing these change of coordinates matrices. Okay, are there any questions on that? Okay, I'll stop the recording.